Everything in your program reduces to execution change in memory. The CPU runs a line. That line writes somewhere. That memory persists after the call ends. State is not abstract. It's stored data that survives execution. When a method finishes, the stack frame disappears. But heap objects remain. So if you mutate something on the heap, you are not just changing a local value. You are changing the system. That is why mutation must be intentional. Trace this literally. Count is 5. The CPU reads 5. Adds 1. Write 6 back into the same memory slot. That write erases history. There is no shadow copy. There is no previous version. Mutation is overwriting memory. It is not conceptual change. It is physical replacement of data. Every assignment operator is a decision to destroy previous state. Now watch what happens. The method receives a reference. That reference points to a heap object. When c.value++ executes, the write happens on the heap. The stack frame ends, but the object remains mutated. That mutation crossed the boundary. It changed memory outside the method's lifetime. Boundaries matter because they define ownership of state. Once you mutate across them, you are affecting something that outlives the call. This method returns nothing, but it mutates shared memory. The list lives on the heap. The write persists. This is a side effect, an observable change outside the method. Side effects are not bad, but they increase the surface area of state change. Now any caller holding that list sees the mutation. Call order begins to matter. State becomes path dependent. This method claims to read, but it writes. Each call increments state. Now the return value depends on call order. This is boundary confusion. A read method should not mutate external state. When reads write, reasoning becomes difficult. Testing becomes harder. Debugging becomes slower. Clarity begins with separating read paths from write paths. Stack variables disappear after execution. Heap objects do not. If you mutate a stack variable, the change dies with the frame. If you mutate a heap object, that change persists across calls. Multiple methods may interact with the same object. Each write builds on previous state. Mutation risk increases with lifetime. The longer state lives, the more careful your boundaries must be. Users call methods, but purity still exists. Notice what happens here. The calculator object lives on the heap, but the add method does not mutate the object state. The stack frame opens. Inputs enter. The CPU computes. A value is returned. The frame closes. The object on the heap remains unchanged. This is still pure execution. Just scope inside an object boundary. Object-oriented design does not require mutation. It requires control state ownership. Design boundaries intentionally. If a method mutates, its name should signal it. If a method reads, it must not write. And the fewer objects you share across boundaries, the fewer places mutate can escape. And the fewer objects you share across boundaries, the fewer places mutation can escape. You're not just writing methods. You are designing where state is allowed to change. That is architecture at its core. Control of mutation.